started last year with this On Things to Come webinar series that aims to introduce ongoing and future space missions to the public, to the general public, but specifically to the scientific community. And therefore, we invite every time outstanding scientists to introduce their mission. Today, we have, as I said, Daniel Müller from the European Space Agency, who will talk about the Solar Orbiter mission. So without further ado, I would like to give the floor to Professor Ip, who, as I said, is the Executive Director of ISSI-BJ, and thank you very much for being here.
Yeah, thank you so much, Lola, and welcome everybody. Today we have Dr. Daniel Müller giving us a talk on the very interesting, excellent solar orbiter mission. And just a few words about this young scientist, Dr. Müller. And he got his PhD from Freiburg. And then after Freiburg, he went to Oslo for his postdoc. And then I suppose then he went to ESA, and then was kind of, you would call it, detailed to NASA Goddard to work on the Soho mission. So he has been I think he never left the sun, right? So now he got what he wanted, on the Solar Orbiter mission, which is in Europe we have been working on it for the last 30 years to get the mission started. So we're very happy to see that this mission coming into being. Okay, Daniel, all yours now. Thank you. Bye bye.
Thank you very much, Professor Ip and Ms. Baldus, for the very nice and gentle introduction. It's a pleasure to be with you today. So good afternoon to Beijing, and good morning to Europe, and very early morning to anyone who's listening in from the Americas. It's a pleasure to present you the latest on the Solar Orbiter mission today. Solar Orbiter is a mission of international collaboration between the European Space Agency and NASA to explore the Sun and the heliosphere. So Solar Orbiter is standing on the shoulders of giants, in particular in the solar domain, the Ulysses and the SOHO missions that have both been missions of collaboration between ESA and NASA. So Ulysses went all the way out to Jupiter to then get over the sun's poles, but at a large distance, to take in situ measurements of the solar wind. While SOHO has been launched in 1995, it is still operating today from the Lagrange point L1, providing uninterrupted measurements of our star. And now Solar Orbiter is the new kid on the block. We launched just over a year ago. And the idea is to take a comprehensive suite of 10 instruments, both remote sensing and in situ, close to the sun and out of the ecliptic plane. So the overarching question is how the sun creates and controls this huge plasma bubble that it blows into the interstellar medium that we call the heliosphere, and in general terms, how solar activity changes with time, and how do we see the changes of solar activity in the heliosphere. So what will Solar Orbiter be providing? We will be measuring the complete physical state of the solar wind, magnetic and electric fields, waves, and energetic particles, as close as 0.28 AU, which is just inside of Mercury's perihelion. And we will complement these in situ measurements with remote sensing data of the sun in the range of spectral windows from the visible to X-rays. And a novelty will be the fact that we will be imaging the uncharted polar regions as we gradually incline our orbital plane out of the ecliptic. And we will combine high-resolution imaging with spectroscopy, and then hopefully be able to link these spectroscopic observations to in situ measurements of ions that gave rise to these spectral lines in the corona. And we'll have a magnetograph to map the magnetic field of the solar surface, and then enable us to extrapolate it into the corona and heliosphere. And for the corona, we have an inner coronagraph called Mattis and an outer wide field coronagraph called a Solo HI. And last September, we published a special issue of Astronomy and Astrophysics that has 17 papers that describe all the 10 instruments, as well as the mission and the general aspects about how we want to operate it. and there's a QR code that you can take a picture of to get to that page. And all these papers are open or free access. Okay, so in a nutshell, we launched on an Atlas V rocket in February last year from Cape Canaveral. We have a cruise phase of just under 2 years that goes all the way to November of this year. So we are now about half a year before the start of our nominal science operations, and the nominal mission phase is sized largely by funding for 4 years. And then the extended mission phase, which is the most interesting phase for the polar science, will take at least 3.5 years. And so the overall consumables on the spacecraft have been sized for over 10 years. But we saved a lot of fuel because we got a picture-perfect orbit insertion by United Launch Alliance, so it could well be that we can operate much longer in the long term. So the orbit is an elliptic orbit with a perihelion, as I mentioned, of just inside 0.3 AU and a period of 5 to 6 months. So we will get the first images of the polar regions a few years into the nominal mission. We'll reach about 24 degrees above the equatorial plane of the sun by the end of the nominal mission, and an even better view at the end of the extended mission over 33 degrees. And an additional benefit of getting close to the sun is that you reduce the relative rotation of the point underneath the observer. So from Earth, you can get a maximum of 2 weeks of coverage if you have, for example, a sunspot rotating from one limb to the next. So from Solar Orbiter, we could track that for almost a complete solar rotation of 1 month because we are partially flying with the rotation. So just to re-emphasize that message, the whole point of Solar Orbiter is to link the in situ and remote sensing observations. That's something that has to some extent been done in previous missions, but because we have the entire payload on one platform, we think we can do new things that haven't been possible before. So in this cartoon, let's look at a flare erupting on the sun. So that has to do with magnetic field topology changes. So the changing magnetic field induces an electric field that accelerates electrons. We will be able to image the flare site in UV and X-rays, and then we will be able to track the escaping electrons because they will emit non-thermal radio emission, and that frequency depends on the local density. So we can track this radio burst with our radio instrument, and the prompt arrival of energetic electrons at the spacecraft will enable us to time the later arrival of heavier ions, and that in turn will show us the magnetic connectivity between the flare site and the spacecraft, and enable us to study the transport of the various ions. So to subdivide this top level question into 4 main themes, we broke it down into these 4 domains of first trying to find out how the solar wind plasma and magnetic field originate on the sun, and then to study how transient events like flares and CMEs drive changes in the heliosphere. And the third question is about solar energetic particles that are relatively rare but very special events that fill the entire heliosphere with very energetic particles. So the sun is really the most efficient particle accelerator that we have in our solar system. And these solar energetic particles can have a real impact on space safety, both spacecraft and astronauts in orbit. So we want to better understand how they are accelerated, how this distribution in the heliosphere works. And the fourth question is about the solar dynamo and how it changes the connections between the sun and the heliosphere. And this has 2 aspects to it: helioseismology, where we study the interior of the sun by looking at small Doppler shifts on the solar surface, a bit like seismology of earthquakes on Earth. That can be done if you have long data sets. And long data sets from 1/2 of the sun you can easily get from space, like with SOHO and SDO, or with a ground-based network on Earth, like the GONG network. But it would be even nicer if you also got the far side of the sun, which we will do with Solar Orbiter. and if you get a better view on the polar region. So in the later part of the mission, we'll do local helioseismology of the polar regions, and hopefully this would help us to better understand the duration of the 11-year activity cycle of the sun. There was a paper by Laurent Gison and co-workers last year where they found that the meridional flow has exactly that right period of roughly 11 years. So it could well be that the meridional flow is really what decides on the periodicity of a star's activity cycle. And to really get a good handle on the return flow deep in the solar interior, you need to get polar observations to see where essentially the direction changes in the polar part of the sun. Okay, early milestones of the mission. So before launch, I would have said that the hardest part of Solar Orbiter was really getting all the instruments built, tested, and integrated on the spacecraft, and to make sure that the spacecraft meets all the requirements of the very demanding payload. But now, a year after launch, I would say probably the hardest part was commissioning a spacecraft and 10 instruments in the middle of a pandemic. So that really required a lot of special dedication by many people, and I'm really proud of all the teams on the operations side and the instrument teams that they pulled this off. Most of the world was in lockdown, including our Mission Operations Center in Darmstadt, Germany, for an extended period. So all of these operations had to be done from people's homes, and that was not envisaged before, but it did work. So that is very good news. And we managed to commission everything on time, which was important because, of course, initially when you're still close to Earth, you have a much better data rate. And so we passed our first perihelion at half an AU in June. And we even got sufficiently, well, better quality data than anyone had expected. So we could hold a first light media event in July and show first pictures and share them with the general public. And we had promised to pursue a really open data policy, so people would get to see the data 3 months after they've been received on the ground. And of course, that's a particular challenge early on in the mission when you get the real data for the first time and need to calibrate those. But by and large, we could really stick to that promise and deliver data to our archive for public usage in September. And I should say that during the cruise phase, the in situ instruments are already doing full science, while the remote sensing instruments are largely operating during dedicated windows for extended calibration and for some special campaigns. And that has to do with the fact that we have fewer ground stations during the cruise phase, but we also need additional time to calibrate the remote sensing instruments at various temperatures relating to various distances from the sun. In December, we had our first Venus Gravity Assist Maneuver, or GAM, to tweak our trajectory to get it closer to the sun. And now later this year, we'll have the second out of 7 Venus Gravity Assists that will nudge the trajectory further to the sun and eventually out of the ecliptic plane. In November, we'll fly by Earth and can wave a final goodbye to a distance of just 440 kilometers. And after that, we'll take a sharp left and head right into our first closed perihelion at 0.32 AU in March of next year. Now, this little animation shows you what I've just tried to put into words in half a minute. So as we revolve around the sun, you see Venus and Earth and Solar Orbiter, and you'll see that every couple of orbits we re-encounter Venus. And this is what we call orbits in resonance. And we pick these so that every time we pass by Venus, we can use the gravity of the planet to slow down the Solar Orbiter spacecraft to make it fall a little further into the sun. And then later on, gradually crank the ecliptic, the trajectory of the Solar Orbiter spacecraft out of the ecliptic plane. So here in a plot, you can see two things. This is distance to the sun and solar latitude above the equator as a function of time. The blue vertical lines indicate the various swing-bys at Venus and one of them at Earth. And what you can see here is that already early next year, we will get really close to the sun. And this kind of distance to the sun we will maintain for many years. So every 5 to 6 months, we have an encounter with the sun, which will enable us to take data with unprecedented spatial resolution and also measure the solar wind at close distances. Not quite as close as Parker Solar Probe, but we have to stay at the distance where we can still operate cameras without them melting away. And the bottom plot shows the latitude. And the interesting thing to see here is that the latitude increase goes in steps. So with each Venus flyby, we crank it up by a few degrees. So it takes a while to get to really high latitudes, but we can do the high resolution close distance science first, and then we can do the high latitude polar science later on. And the third row is a slightly more complicated plot that's in so-called geocentric solar ecliptic coordinates. So Earth as the blue dot is fixed and the sun as the yellow dot is fixed as well. And what we see is that in the first part of the mission, the perihelia occur roughly in quadrature. So we are closest to the sun when we can see solar orbiter sideways from Earth or near Earth. And later in the mission, we'll have every other perihelion on the Sun-Earth line, which is interesting because then you can co-observe the same area on the sun from near-Earth assets. Okay, so coming to the spacecraft is all about thermal control. We go to roughly a quarter of the distance to the sun. So the heat flux goes with the inverse square of the distance. So we'll have more than 20 kilowatts per square meter to deal with and make sure that the sensitive electronics can live with it. And our approach was to have a massive but still very light heat shield of 2 layers. And the remote sensing instruments are looking through holes in this heat shield. And these holes have shielding doors for extra protection. We also have solar arrays that we tilt. So we can adjust the tilt angle, so we just get enough power, but at the same time keep the solar arrays only modestly hot. And we keep the in situ instruments mostly in the shadow of the heat shield on an instrument boom, which makes them also be as far away as possible from the any noise generators on the spacecraft, like camera mechanisms or heaters. And we have one remote sensing instrument that's here, the heliospheric imager, and that is looking over the edge of the heat shield to image a large patch on the sky, including the solar wind. And we have 2 in situ sensors that look over edges of the heat shield. These are part of the solar wind analyzer suite. So the heat shield is really the most ingenious part of the spacecraft. It's different from the approach taken by Parker Solar Probe, and that had to do with the fact that we needed holes in our heat shield, and also the fact that we had a special coating called solar black, which is a surface treatment that we use for the titanium multi-layer insulation that we wrap everything in, and that is chemically or energetically completely inert to a bombardment by particles. So we know that the thermal conditions will remain the same. So some people have asked, why didn't you make it white? There is work in progress to also make a white version of it, but you never know whether white will stay white all the time. And rather than having to deal with a degraded surface performance, we'd rather have a stable and black layer that will simply maintain the same optical qualities or thermal qualities through the mission lifetime. So the whole thing looks a bit like a sandwich with toothpicks that has lost its filling. So we have a bottom layer, which is an aluminum honeycomb panel, and that is wrapped into a carbon fiber composite, wrapped into many layers of thin titanium foil. And then we have these so-called star brackets that are titanium brackets that are star-shaped, and they hold a relatively thin and floppy contraption of about 30 layers of titanium foil, and the outermost foil is coated with this solar black process. And the concept is that we'll have temperatures for up to 520 degrees on the front side and less than 50 degrees centigrade on the backside of the lower panel. And that is what we need to keep the instruments at operating temperatures. So we have a large toaster at ESTEC, the European Space Agency's Technology and Research Center in the Netherlands, where I work. So here we lower the engineering model of the heat shield into this toaster. That was a long time ago, but it also shows you how long it took really to build Solar Orbiter. Then this big lid that you can see on the left was closed, and it was illuminated with an array of 25 kilowatt xenon light bulbs to really simulate the conditions in orbit. And ultimately, it was deemed fit for flight. And this is a last picture of the spacecraft before it was shipped to Cape Canaveral for launch. You can see that all the appendages are folded in, and all the heat shield doors are closed. But you can also see that these various parts of the heat shield are really put in place with Velcros, and have the right cutouts, so to make sure that the in situ instruments can still observe the energetic particles coming from the sun. The second engineering challenge was really to make sure the spacecraft is as invisible as possible to the in situ instruments. We've had lively discussions between our principal investigators and the people who built the spacecraft, and effectively the engineers said, well, essentially you want us to make the spacecraft disappear. And the PI said, yes, that's exactly what we want. So they said, okay, we'll do our best. For example, they wrapped the reaction wheels that we use for maintaining 3-axis stability in a mu metal enclosure to make sure that the varying speeds of the reaction wheels do not become visible in the magnetometer signals. And we wrap the rear side of the solar arrays into conductive foil to make sure that they don't charge up in the solar wind and then essentially create an electrostatic bubble that would deviate the low energy electrons that would otherwise hit the spacecraft. And in addition, we put an onboard contamination system on Solar Orbiter to make sure that we would detect any deposition of molecules or particles next to the apertures of sensitive remote sensing instruments. And it looks to be working quite well, and that's, of course, a big relief for all of us. Now, I want to walk you in the next 15 to 20 minutes through the 10 instruments on the mission and interleave a couple of early science results. We have a special issue planned with the let's say, first real science, and the papers are being submitted right now. A few are actually already available online, mostly from the energetic particle suite. But I just wanted to give you a flavor of where we are. So the engineers always said we had a very busy spacecraft, and that was a bit of a criticism, at least I heard it that way. But the point is, I mean, we really had to fly all these 10 instruments because they are all doing unique aspects of the science we want to do. So I'll first walk you through the 4 in situ instruments. So the energetic particle suite measures, as the name says, the composition and timing of energetic particles. We have 4 different sensors. Some of them even have multiple sensor heads. And we have a rather complete coverage of energy from electrons all the way to heavy ions like iron. And many sensors look in the average Parker spiral direction. Some look opposite it, and some look in other parts of the sky. So we could already measure particle fluxes during the entire orbit. The sun is, of course, relatively quiet at this part of the solar activity cycle, but we caught some interesting small solar energetic particle events a few months ago. And another thing that was really a serendipitous event was Solar Orbiter crossing the trajectory of Comet Atlas, or what used to be Comet Atlas. So the jury is still out on that one. Unfortunately, the comet disintegrated before we could really fly through its tail, but nevertheless, it seems as if we got some data that indicates interesting things that could be explained by some aspects of the comet tail still being intact. Then we have, as a second instrument, the magnetometer with Tim Herbury SPI. The magnetometer measures, as the name says, the magnetic field with high precision. We can, for example, do multi-spacecraft studies of CMEs. Here, forthcoming article by Davis et al. With the Bepi-Colombo spacecraft. And an interesting aspect is to map the magnetic field on the solar surface to the spacecraft and then see about the connectivity. And with our international fleet of spacecraft, we can really do a lot of interesting things. So this was a CME in April last year that was virtually a non-event as seen from SOHO and Earth, the so-called stealth CME, but it was nicely seen from stereo A, which was looking sideways, and Solar Orbiter just happened to be upstream of Bepi Colombo, which happened to be near Earth. So that was a unique configuration to size and measure the CME. Now, I mentioned radio emission earlier on. We have an instrument for that called RPW, Radio and Plasma Wave Instrument, that has 3 antennas, 6.5 meter antennas that were nicely stowed in this little box before deployment. And they measure the electric field and the solar wind. And we have a surge coil magnetometer that complements the magnetometer mag by measurements in the higher frequency domain. So there's lots of interesting solar wind physics in these electric and magnetic field frequency ranges. And probably the most complex instrument suite is the solar wind analyzer. And it has 3 different parts. We have the electron analyzer system at the end of the boom that has an almost omnidirectional view of electrons coming to the spacecraft. And we have these 2 parts looking over the edge of the heat shield, the heavy ion sensor of SWA and the proton and alpha sensor here at the bottom. And in overall, they cover the complete state of the solar wind particles from below, well, a couple of EV up to 80 keV per charge from the HISS instrument. And there it stretches into the regime where then the energetic particle detectors take over. So what the HISS instrument will be able to do is provide us with energy per charge maps as a function of time of flight. So this is an early map that shows you all the various ionic species from protons all the way to iron 8+, and they nicely map along this plot as a function of time of flight. So the SWA instrument had some technical difficulties with their data processing unit, so they have not been operating as much as the other instruments so far, but the good news is that we are recommissioning these sensors now one by one, and 2 of the 3 are already been evaluated to be fit for science operations in the last few days. So there's new and more science coming from SWA very soon. Okay, now moving over to the remote sensing side, we have 6 instruments. We'll start from the sun and then move outward. We start with the visible light polarimetry with the Phi instrument. And that was built by the Max Planck Institute for Solar System Research in Göttingen, with Sami Solanki as the principal investigator. So the point of Phi is that it can measure the magnetic field vector using Zeeman effect, and the line of sight velocity using Doppler shifts in the solar photosphere. And that is essentially the starting point for all magnetic field extrapolations. It has 2 telescopes, one to take full disk images and one to take high resolution images. And even though the image is small, you can see that it has an excellent quality. You see all these solar granules here. Each has a diameter of roughly 1,000 kilometers. And because we are a deep space mission, we don't have the luxury of very large bandwidth because we are really far away from Earth most of the time. So what they had to do is really invert the polarimetric data on board to generate physical quantities based on the 4 Stokes parameters. And that is something that has never been done before. Usually you do this radiative transfer inversion on a computer and you tweak the parameters until you get the best fit. But they have to do everything on board. So that's a first, and it seems to work. So here are the first inverted HRT magnetogram. There's a lot of quiet sun here because we are in a low activity phase of the cycle, but activity is picking up now. And I should mention in May, there's a special ISSI-BJ seminar by Sami Solanki, so I'm sure he will talk in more detail about his instrument. And then moving out into the sun's corona, we have the extreme ultraviolet imaging instrument, or EUI, that is a set of 3 telescopes, 1 full sun imager with 2 filters, 17.4 nanometers, which images the sun at roughly 1,000,000 degrees. That's iron 9 and 10. And helium-2 304, which images the chromosphere, so the layer above the photosphere of around 22 to 50,000 Kelvin. And then it has high-resolution imagers that have a plate scale of half an arc second per pixel. So that's the same plate scale as the AIA instruments on the Solar Dynamics Observatory, but because we'll go in to 0.3 AU, we'll roughly get a factor of 3 to 3.5 higher spatial resolution when we add perihelion. So EUI is let's say the poster child in terms of providing images that you can also show to the general public and make them interested in the science that we are doing. We'll try to get images of the sun from Solar Orbiter virtually every day as we move into the nominal mission phase. That's the full disk imager here. Now in February, where we're exactly behind the sun as seen from Earth, so we can image that as well. The cross here shows you where the sun-Earth line is on the other side. We have a Lyman alpha high-resolution telescope in 121 nanometers. We had these interesting features that have been called Campfires, which are very small-scale flares that we are still trying to investigate to find out whether they're really something new or just smaller versions of things we know already. And we can try to really map the solar wind measured at the spacecraft back to its sources on the sun, like, for example, a polar coronal hole. So these were these campfires that were mentioned in the first Light Media event last July. These are really tiny events, but the thing is, they happen all the time in all quiet sun conditions. So they look like tiny versions of flares. And the question is, are there sufficiently many of those that they are energetically important enough to potentially play a role in heating the quiet sun corona? So this is something that I'm personally very interested in, and we'll try to find out more as we get more data. We got just about 50 frames last June, but we'll get a lot more as the mission goes into the nominal mission phase. Now, images are nice, but what's even nicer if you have spectra, because then you can start doing more physics. So we have an imaging spectrometer called SPICE that is using a spectrometer slit to generate spectroscopic images. It has 2 channels, and it can image lines from ions that we can then measure in situ with the solar wind analyzer. So that is very nice for the connectivity. And it has already gotten some interesting results, peculiar brightenings in the transition region. So these are small things that persist for a long time. We don't know exactly what they are yet. They could be related to the blinkers that the CDS instrument on SOHO has been observing about 20 years ago. But we'll try to find out more, because that's really where the physics lies. We want to overlay the images that we get from EUI and also from AIA at a different angle, and then measure the Doppler shift, and from that determine what the real motions are of the plasma, and from the various spectral line measurements from different ions also determine the density of the plasma. So now we move out into the sun's corona. We have an inner coronagraph called Mattis. So it has a visible in the UV channel, and from a technique called Doppler dimming, you can determine solar wind speed just from these remote sensing observations. And with these 2 channels of Lyman alpha and polarized visible light, you can also determine thermodynamic evolution of the CME plasma. The X-ray instrument STIX images our, well, let's say, hot contribution of flares and flare accelerated electrons above 10 keV. The good news is that we figured out that STIX could really be operating continuously, because it doesn't take a lot of telemetry and it doesn't take a lot of maintenance. So that instrument is now catching every single flare that it can observe from Solar Orbiter's vantage point. It can then decide which ones to downlink. And there will be a seminar by Sam Krucker at ISSI-BJ on the 19th of May. Now, for the big picture, we have the Solar Orbiter Heliospheric Imager built at the Naval Research Lab in Washington, D.C. The development phase principal investigator was Russ Howard, who's built most coronagraphs that at least I'm familiar with, starting in the 1970s and now more recently with Stereo, Parker Solar Probe, and SOHO. And he's just handed over to Robin Colanino, who's the new PI, because Russ has passed the typical retirement age already long time ago, and now he said it was about time to really focus on science and leave the mundane tasks of managing the instrument to younger people. So SolarHigh looks over the edge of the heat shield and detects a large array of the sky of 40 by 40 degrees and looking about 5 degrees off to the side of the sun. So this is a pre-launch simulation where the fields of view of SolarHigh and Mattis are indicated, and you can see as a function of time how the scale changes, and you can also see the different modes in which the wide field coronagraph can operate, because also here we have limitations in telemetry, so we can bring down either a smaller number of big frames of the entire detector or just focus on particular areas of the detector and bring them down with higher time resolution. So, and this is now SolarHigh in orbit. As I said, it's not operating all the time in cruise phase, but this was a time when it was operating for calibration, and we got a nice family picture of the inner solar system of Venus, Earth, and Mars. Venus at 48 million kilometers, Earth at 250 million, and Mars at 332 million kilometers distance. And we made that available to the general public, and immediately people looked at it in more detail and looked at the stars and also looked at small features that they felt were not stars. So they asked questions about what do we see here? And it was interesting because of the configuration. So this is where Solar Orbiter was at that time. We actually have a website where you can find out yourself every day where Solar Orbiter is. So we look into the inner solar system with these 3 planets, but there's more. And it actually turned out that there's also Uranus at a distance of more than 3 billion kilometers visible in the field of view. Just very faintly, but it does move slightly differently from the star field in the back. And even if you look at the Earth more carefully, it turns out that Earth has a little bulge to the right, and that seems to be caused by our moon. So I find that quite nice because it shows really also to the general public how far away we are, and that we are really exploring and flying through our solar system. Now, about data, we have a limited subset of data that we call low latency data. These are really just tiny snapshots to show how things work and to be able to adjust operations accordingly if they shouldn't. That we call low latency data. That's coming down with every ground station pass. So right now, 3 times per week, and as of November, every day. And so these are all publicly available, and I think can be also interesting for some limited science as well, for example, for space weather. Public release of science data started in September with the first 3 instruments, and then in December, the solar wind analyzer data followed. And the EUI imager pursues a very open data policy in particular. So they've already put all their engineering data from the commissioning phase out to the general public as well. And we have a Solar Orbiter data archive called SOAR, where all the data is stored and made accessible to everyone. We have science web pages where you can find most of the things that I linked to earlier in the talk. In particular, the Where is Solar Orbiter tool, our publications, and also recent images and animations. If you're interested in details of the mission planning, also that information is available to the general public. There are web pages here from the Science Operations Center, or SOC. And on the science side, we maintain a top-level science activity plan where we outline and describe in more detail the various science cases that we want to tackle, which then get worked into distinct operations plans by our Operations Center colleagues. Now, I hope I've convinced you that there's a lot of synergy between Solar Orbiter and other observatories. So we now have a fleet of missions in orbit, which is really a unique period of time for all of us to use these data together. So there's great potential to do things as a team. We have a good and vibrant science community. There is a session of the European Geophysical Union coming up later this month, where we'll present first science results, some of these that are now being submitted as papers to the A&A special issue that's coming out this fall. And we put in place 9 in situ science working groups that are chaired or coordinated by Daniel Verscharen, who is at Müller Space Science Lab just outside of London. And everyone is welcome to join those. There's a fixed slot of 2 hours every Thursday. And you can sign up to any of these 9 working groups that you are interested in. And they meet roughly once a month, always on this Thursday slot. And every 5 weeks, there's a summary that presents the overview of the last month. And as I said earlier, there's a special issue with all the instrument and mission papers that came out in September. Now, I want to close really with a word on the team aspect. Solar Orbiter is absolutely a team effort. We couldn't have done it without hundreds of people that each did their part. And the few people that are here are PIs, but also representatives of the funding agencies of our member states. And it's really something that took many years, and at least it took me more than 10 years and more time than I thought it would to see the mission get into orbit. But here it is now. A year ago, we thought the world might not look the way it does today. So we have science meetings that are now no longer in person. But at the same time, it has a certain advantages, because it made it much easier for me to be virtually in Beijing today and still pick up my kids to school later in the afternoon. So that is good. So maybe we can maintain some of this in the future, because it clearly makes the science community come together on a global scale. And with this, I would like to close. Just a little animation that sees Solar Orbiter getting close to the sun, and hopefully make a couple of really interesting observations that we all can work on in the years to come. So with that, thank you very much. I'm done. I'm open to answer any questions you might have.
Thank you very much for the outstanding presentation, and also for promoting the Solar Orbiter webinars that we will have in May. We have indeed the first question that you can see if you want to read it in the chat box. There is any plan to work with China's ASOS Solar Telescope mission?
Absolutely. So we've had invited presentations from missions like this one, and also another mission from India that's coming up in the next few years. So we absolutely want to explore all these international cooperations, and we're in particular thinking also about let's say PhD student schools, where we can really explain to young scientists what we have to offer, so they can really see for themselves what they can use in order to promote, or take their science further. But indeed, I think there's great potential in putting these various missions to work together, because ultimately the data doesn't really care where it comes from, but I think we all put our data on the table together for everyone to use, and I think that's the best use of all our resources.
Thank you very much. While we wait for other questions, I had someone contacting me during the talk, so I'm sure there are some more questions. I would also like to point out that there are almost 2,000 viewers at the moment, so questions should come up. There is, in fact, one comment from Hugh Hudson, congratulating you on the great success. And the question is, are you really serious about campfires and coronal heating? Aren't they too sparsely distributed in both space and time to be relevant to the global corona?
That's an excellent question, Hugh. The honest answer is, I don't know. I mean, our first thoughts were that let's say the media echo on campfires was much larger than anyone had expected, in particular the PI. It seems, I mean, no, it seems that this is, we should not try to do let's say solar dermatology and give little things new names unless we are really sure that what we know what it is. So honestly, we don't know yet really what they are. There are a couple of papers forthcoming, including with stereoscopic observations from SDO. So I think that's very interesting. Clearly, it allows us to look into smaller scales. From a physics perspective, I would not expect for the physics to change significantly just because you look into a smaller scale. But I can't answer the question yet on the statistics. We simply don't have enough data yet on the occurrence rate of these small events and their, let's say, stability over time. So I don't know. We hope to find out, of course, soon, and hope to answer that question better in let's say, the next 1 or 2 years.
Thank you very much. There is a new comment from Fabio Reale. Any scheduled event about early mission results?
Can you repeat the first part of the question?
If you have any scheduled event about the early mission results.
Okay, so the original deadline for these papers was in January, and we relaxed that a little bit because due to the COVID pandemic, people clearly have, let's say, certain challenges to do all the work that they have to do in a given time. So we have the last papers coming in this month, and then it's just a question of the usual refereeing process and how long that takes. The goal would be to have the full issue of first results papers published formally online in the fall of this year, and we will clearly accompany that with activities where we highlight, let's say, some of these results also to the general public. And as I mentioned earlier, the A&A special issue is an open issue, so there are some papers that were already submitted end of last year, and they can already be accessed now. So as results get peer-reviewed and accepted, they get put on the webpage as pre-publications, and in addition, people might choose to put them onto archive as well. So anything that is accepted is available online. And once we have the whole package accepted, then we will do some sort of event to highlight, let's say, the first set of results to the general public too.
Thank you. There is a new question. Any isotope measurements with the solar wind instrument?
Well, we have, I think the best is to look at the solar wind analyzer paper that specifies in detail what ionic species we are observing. Or alternatively, the co-PI of SWA, that is the principal investigator of the heavy ion instrument, is Stefano Levi from Southwest Research. So he would probably be the best to answer that particular question.
Okay, thank you very much. We still have 10 minutes, so if anyone wants to ask any question, this is the time to do it. Professor Ip, if you also have any question. Professor Ip?
Well, I'm not expert on the sun, right? But then I'm very happy to see that, very, very fantastic observations, and there are other people on the audience. I can see a lot of other experts. So I would encourage them to ask, to give Daniel some hard time, give him some difficult questions.
They are indeed. There is another question, a couple of other questions. The first one is, do you have any observational campaigns with the Parker Solar Probe?
Absolutely. So we are in close contact with the Parker Solar Probe team. Of course, in the current cruise phase right now, we are the top priority is to get all our remote sensing instruments fully calibrated and ready for the nominal mission phase that starts in November. But we are already now trying to schedule extra observations at times that are most relevant for Parker Solar Probe, in particular to provide the imaging context that Parker Solar Probe does not have. So Parker Solar Probe has a wide field imager, but of course, given the extreme orbit, it cannot look at the sun directly. So we are trying to do that for Parker Solar Probe and do science together. And there's a lot of collaboration already between Solar Orbiter PIs and Parker Solar Probe PIs to exploit both missions together.
Thank you very much. Masaki Nishino, really great talk. Do you have any special observations for Saturn phenomena such as coronal mass ejections?
Well, absolutely. I mean, the one thing is that originally Solar Orbiter was baseline to have only 3 windows per orbit of 10 days to use the remote sensing instruments. And that was driven by the limited telemetry available. But of course, from the physics perspective, it significantly reduced the likelihood to detect phenomena of which you don't know the timing. So probably the best surprise that we got in orbit was that the de facto telemetry rate of the mission is significantly higher than the baseline. And so that means that we will be able to have at least what we call synoptic data for hopefully the entire orbit as we enter the nominal mission phase. So that will hopefully help us to detect many more coronal mass ejections than originally foreseen. I should mention that the inner coronagraph Mattis has a certain constraint with respect to off-pointing. So we can point the spacecraft bore side to any point on the sun. But if we are too close and we point it to the limb, then the Mattis coronagraph gets too much stray light into its aperture, so it can't operate. So we'll try to have, let's say, a good balance between disk center pointing, where we can get chronographic images from Mattis, also at close distance, and also doing particular campaigns where we look, for example, with high-resolution images at the limb of the sun or tracking active regions. But in general, I think this new and improved concept of having synoptic data throughout the orbit will really greatly enhance the chances of getting CMEs. Of course, it will not have, let's say, the temporal cadence all the time to really track the evolution properly. But we have essentially a whole library of science cases in this mission-level science activity plan. And some of those are dedicated to studying the details of CME. So we will do something like the CME watch program on SOHO to simply look for CMEs at certain times when we hope they'll occur.
Thank you very much. Upcoming question is ESA thinking about organizing a new solar mission? And if so, what would that be?
It's a good question. Maybe I can relay it to our national funding agencies to tell them that they should really start thinking about the next generation mission now. In the near term, there is no science mission concept that is let's say, being pursued yet. There is, let's say, an open call for ideas for, let's say, the time frame of 2035 to 2050. So that is still proceeding. But I should say that in the next few years, there's a mission that is being considered more from the space situational awareness standpoint and operations. And there, the idea is to be at the Lagrange point L5, so to be relatively constant in sun distance, but at an angle with respect to the Sun-Earth line. And that mission would double as a solar mission, even though it's not, let's say, driven as a science mission, but more as an operational mission. That should be able to provide us with more and with an additional vantage point and more solar data in the time frame of, let's say, 5 to 10 years.
Thank you very much. There is someone asking about turbulence studies, but the question is not clear. So I'm waiting to see if this participant can explain a little bit better what he or she means with the question. In the meanwhile, again, since we now have around 5 minutes left, as you mentioned during the talk, we will have other 2 webinars on the Solar Orbiter mission, one with Sam Krucker on May the 19th, and then we will have Sami Solanki on the 25th of May. And before these 2 talks, we will have next week Stefano Vitale from the University of Trento, who will talk about the LISA or LISA mission, which is a spaceborne gravitational wave observatory. So waiting for the maybe last few questions. If not, if Professor Ip, do you have anything to add? And if not, maybe we can conclude it here.
Well, yeah, I just want to say that I want to thank Daniel for this, very, very, very interesting talk. And then I hope that giving you another year, you'll come back to tell us all the very interesting, exciting results you collected in the beginning of the mission. And I also want to ask the participant, the audience, that if you have any comments, that suggestions or new talks, or like Daniel, if you want to volunteer your colleagues not to give talks, please just send us the suggestion. Mm-hmm. And then this platform is open to everybody, to international scientific community, just a survey of communication and information exchange. And then that's all I want to say for now. Mm-hmm.
Yes, thank you very much. Indeed, we have a quite rich lineup until July. / September, but of course, especially for the ones I can see all the scientists in the chat, if you have any suggestion or you want to propose a topic related to space missions, we are always open to new ideas. I would like to thank once again Dr. Müller for the outstanding presentation that was recorded and will be online in the upcoming days. And thank you once again to everyone, the ones on Bilibili, the ones here on Big Market, for participating and interacting with Dr. Müller. Have a nice weekend. Thank you.
Thank you.
Bye-bye.
Thank you so much. Yes. Daniel, thank you. Yeah, bye-bye. Bye-bye, everybody.
Bye-bye.